Welcome to Megasquirt Training Part 15. In this video, we're going to be taking a look at our open loop idle control. We're going to have a lot to learn, so let's get started. Okay, so let's jump into this video and talk about our open loop style idle control that we're going to be looking at in our Tuner Studio software. So we're going to be finding we have the ability to control an idle control motor, and that's going to allow us to vary our idle speed, whether on a cold engine or on a warm engine. It's going to allow us to have some idle airflow bypassing our throttle plate. Now we're going to have two forms of idle control motors. We're going to have a stepper motor and we're going to have a pulse width modulated motors. We're going to be finding these are very common, found on a lot of engines. So our Megasquirt or our Microsquirt is able to control one of these control solenoids, and we're going to be able to use it for our idle control. So there's going to be a whole bunch of things that we need to set up. We're going to be finding that this open loop method is very, very simple and very effective, especially if you're using it just to assist for cold starting. So you don't have to keep your foot on the throttle. If you have a race engine that you're currently having that problem where you can't fire it off cold without keeping your foot on the throttle till the engine warms up. So we're going to have a lot to cover in this video, so let's jump in so we can check it out. Okay, so let's get started here. We're going to be talking about using our open loop style idle control to control our idles. So if we have an idle control motor that's going to be installed on our engine, we're going to be finding we either have a pulse width modulated style idle control motor or a stepper control motor. Now, typically a pulse width modulated idle control motor will be a two-wire. One wire will go to power, the other wire will go back to the Megasquirt, and we're going to be sending a pulse width modulated output to that solenoid to operate it at a percentage of duty cycle. This is going to be similar to how we control a fuel injector or a boost solenoid. Now, if you have a stepper motor, you're going to have multiple wire, either 4 or 6 wires. It's going to be a little bit different in configuration, and the number of steps that the motor is going to make is going to allow more or less airflow in to the engine. And you're going to be finding with a pulse width modulated, the more or less duty cycle is going to allow more or less air in the engine. So our goal here with the idle control is to get air bypassing from the throttle plate so that we can maintain our idle speed. Now in the open loop style format, I typically go and try to set up my warm idle. So after my engine's been warmed up, I go in and I set up my throttle stop on my throttle body so that I have little to no idle control motor output to allow me to achieve that warm idle speed. I'm only interested in using my idle control motor for cold start purposes. I find that by not utilizing the idle control motor on a warm engine and setting up my ignition advance for a feedback we're going to be taking a look at here provides a much more stable idle, especially on a race engine or an engine that has big cams installed or big injectors. So this is going to be something that you're probably going to want to implement in your tuning strategy. So the very first thing we have to do is go up to Startup Idle here, and we're going to be moving down into Idle Control. If we click this, we're going to be finding that right now my idle valve type here is set on None. Now first I'm going to go over using a pulse width modulated valve. This is going to be the easiest way to go about using the idle control. There's going to be a lot less things that we have to set up, and it's going to be a much simpler configuration. If you're going in and you don't have an idle control motor at all on your engine and you want to add one, so you want to have cold start so you don't have to keep your foot on the throttle, which is kind of getting really annoying after a while, you could simply take something like a Honda idle control motor valve from a D, B, or H series engine. They're a simple 2-wire design, and you can make an adapter plate, and they have a feed and a return for the way the motor works. So one side of the motor is going to be able to take the vacuum from the intake manifold, and the other side of the motor is going to be putting it out into the atmosphere. So it's going to control that controlled vacuum leak. It's pretty much the easiest way to add a idle control motor to your engine. I do it quite frequently with an engine that's a race motor that wants to have cold start assist. So pulse width modulated valve here, if we click it, we're going to be finding that it's going to require me to have a power cycle. So I'm going to power my box down real quick. I'm going to be patient, and I'm going to go ahead and power it back up again. That's going to give me this warning message. I didn't burn that before I went and I cycled my power. I'm just going to click burn there, and it took that change. Okay, so the next thing we're going to be seeing here, we have this algorithm. We see open loop and closed loop. Now in this video, we're only going to be using this open loop style method. I'm going to be going over in a separate video the closed loop. It is a lot more complicated. I don't normally use the closed loop method because it introduces a lot of things that we have to program and keep track of. And it's much, much more simple, as you're going to be seeing in this video, doing the open loop method. And this is primarily how I set up my idle control for Megasquirt.
So if we move in here to our pulse width modulated idle, we can see our crank to run taper time. This is going to be specifying how much time it's going to be taking going from our crank to run mode, and it's going to be transitioning our idle control motor in from the crank mode into the actual run mode. We're going to be looking here, we're going to be seeing we have a cranking table and a warm-up duty table. So it's going to be transitioning the amount going from the reported value here of duty cycle from our cranking mode and how long it's going to be taking to go up into this warm-up mode here into the duty cycle. You can see there's a much different values. I think looking here, jumping back here at a warm coolant temperature, let's jump into our cranking. We can see here at 175 coolant temp, we can see 40% duty cycle, and see here at 160 temp, 2% duty cycle. So there's a really large change in our duty cycle. We need to have a little bit more, jumping in here real quick on the cranking, we need to have a little bit more values here to give more airflow bypass on a cranking condition than we do on a warm engine when we get it running for duty cycle, so allow less airflow in. We're going to be taking a look at these here, but that's what this is going to correlate to. Let's close this again. We're going to be finding that it's going to specify how long it should hold the value from the crank table until it tapers it in to the actual run table. So we're going to be dialing this in as needed. If we want to have a higher idle speed or a little bit more starting assist when we're actually cranking, it's going to be the equivalent of us giving it gas or more throttle. If we find that we have to give the engine throttle to make it fire up, we might have too much cranking fuel because by giving it more throttle, it's going to be leaning out the air-fuel mixture, as well as going here to the crank to taper. If we go and increase this value, it's going to go in and utilize that duty cycle or more airflow, which is the equivalent of us putting our foot on the throttle. So that's something to keep in mind. Our valve mode here, we can see we have a normal or inverted. Almost all pulse width modulated style idle control motors are going to be normal, so 0% duty cycle will be off. The idle control motor is not going to be doing anything, and 100% duty cycle will be the idle control motor all the way open, allowing all the airflow to bypass and have that controlled vacuum leak. So this is typically going to be set on normally 0%. Run valve before start. If we set this to a value of on, it's going to look with the key on, engine off. It's going to go in and utilize the values here from our cranking duty table. This can help us on starting. You're going to be finding the first few cranking revolutions. If we do have some percentage duty cycle sent out to the idle control motor, it's going to be again kind of having that equivalent of keeping our foot on the throttle a bit, and can help us go in and start to have a little bit faster idle. So you may want to leave this off and then experiment with turning it on. It's going to be up to you how you want to go ahead and handle that. Our pulse width modulated idle port, we can see it's F idle. We're going to be finding that this is going to be where we pretty much always want to have our idle set unless we've used it in the calibration file for another output. If we're going to be using idle control, I suggest that you just use this F idle here alone for idle. We can see we have some other choices here for remote ports, but typically speaking, we're always going to use this just for idle speed. Lastly, we're going to be finding our valve frequency here, and we can see it's set at 92 Hertz. We're going to be able to select different frequency types. So depending on what kind of idle control motor you're trying to control, you're going to be finding it operates at different frequencies. So if we have a Bosch or a Ford pulse width modulated output for the idle control, we're going to be finding they go between 50 to 100 Hertz. So we might experiment with some values here. If we have something like a Miata, that's going to be running here close to 300 Hertz. Something like a Honda idle control motor, between 250 to this 313 Hertz. So you can experiment with what's going to work best depending on what you're using there for your actual solenoid to control things. Let's click burn, and let's close, and let's jump into our startup idle. So getting back to our idle cranking duty table steps, or the duty/steps, we can see the duty cycle is going to be applicable to our actual idle control motor selected for that pulse width modulated output. If we're going back in here in a second and going to be setting up and looking at our stepper motor, that's going to be corresponding to the steps. So the values that we place here in the table are going to be different based on what we're trying to control. So we're going to be seeing here, this table is based on coolant temperature versus the duty cycle. And what we need to do here to make this a little bit easier, let's go right click. We're going to be looking at outputs, and we're going to be looking here at our idle pulse width modulated gauge in this mode. And we're going to be finding that we're going to be utilizing whatever is reported in this value here under cranking. So I'm going to bring my engine up into cranking condition here real quick. And we're going to be finding here, let's go ahead and bring it up slow so we can illustrate this. So we can see here, bringing our engine RPM up into our cranking condition, we're showing that we're at 255 on our crank speed, Our idle pulse width modulated is coming from this value here, 175 coolant temp breakpoint, we're at 196 coolant temp, and 40% duty cycle output. If I go and change this to something like 50, we can see that it's changed there. Change it back to 40. Let's click burn. It's going to go back. It's going to go and reset the ECU, and it's going to go back to that value. Let's go ahead and actually set this to 40 real quick here. We can see that changed it. Every time I hit burn, it's restarting the ECU, and that's why you see the pulse width modulated dip. So whatever we program here, this is going to be used under cranking. We want to have a high enough value here that it allows us to fire off the engine, but we don't want to have too high of a value where it causes the engine to maybe have really high starting flare. So the engine RPM might go all the way up to something like 2,000 RPM and then come back down again. So we want to have just a balance of this value here, and it's going to be pretty straightforward. Now, once we come out of our cranking condition, let's jump up to our next table here, open loop table. We're going to be finding 160 coolant temp. It should go to 2% duty cycle on the output here. So let's go ahead and I'm going to bring my engine RPM up. And we're going to be finding right now I am in my run mode. And we can see the pulse width modulated tapered out. So it went from that value of 40, it tapered all the way out here to 2%. And that was related to, jumping in here real quick so we're clear, the crank to run taper time. So a half second. So it took a half second go from 40% duty cycle, taper back down here to 2%, which is coming from the table here. So this value is going to be your warm idle controlled duty cycle value. So depending on what your coolant temperature is at, if we bias our coolant temperature here, if we bring our coolant temperature back, we're going to be seeing come up to some different temperatures here. Let's say 76, 77 coolant temp. We're going to be finding that the pulse width modulated output is between 60 and 80. It's interpolating between 12.5 and 10.6%. So that's why we see our output here at 11%. So that is what our output's going to be sent on our cold engine. We want to go in and set this idle pulse width modulated value on a cold engine, something like 77, 76. We might have to have a high value here, depending on how sensitive that control is from the output here. We might be at something like 50 or 80. At the colder temperatures, we might be at something like 90. Typically, I don't go much higher than a value of 90% duty cycle. You're going to be finding that going from 90 to 100 really doesn't flow that much more air, and it doesn't really help a whole lot. But this is going to be absolutely something that we want to set up. Now, once we get up to the warm temperatures, let's go ahead and bring our engine up and warm up our coolant temp. Let's bring it back up here to, too hot. Let's go ahead and bring it to, let's say 160s or 160, 170s are a warm-up temperature here. We can see, again, we drop back to 2%. Now, what we want to do here is get our idle throttle stop on our throttle body. We want to increase that throttle stop so that we have enough air coming in that we don't have to rely on this pulse width modulated output to do much of any control. We want to turn that screw in going upwards and increasing that throttle plate to get whatever our desired air fuel is, or I'm sorry, desired RPM is. So we can see it's 767. Let's say we turn our idle screw up here. We can see that our idle RPM might go to something like 1,000 or 900, depending on what we want to hear. Let's say, let's get it up to roughly 900. We can see it's 885. That's close enough. So we have our idle set with our idle throttle stop, and we find that we have little to no duty cycle output here. We could even drop this back to something like 0. We can see if we do that and update it, it drops to 0. So now we're relying on the engine idling on its own mechanically. The amount of airflow coming in past our throttle plate is going to be how much airflow is dictating our idle speed. Now we are able to go in and set up another compensation factor in the background, which is something that I always recommend that you do. We can use our ignition timing to either increase or decrease the amount of torque at idle. So if we advance our spark timing, we're going to be finding that our torque is going to increase, and if we decrease our spark timing at idle, we're going to find that our torque will decrease. So our idle speed will decrease. So an increase in torque, increase in idle RPM. Decrease in torque, decrease in idle RPM. So it's pretty straightforward, but what we need to do to make this work, jumping in here to start up idle, if we go to idle advanced settings, we're going to be going in here, and up top, we're going to go to idle advanced on, and let's just set this. We can see there's going to be a couple different things that we can set this as. Now, what we need to pay attention to here before we go any further, let's go ahead, let's close these two tables out. Let's open our spark timing table up. Let's jump in here, and we're going to be looking at our values in our spark timing table. Now, the values here, we can see it's interpolating between 80 and 70 kPa here at roughly 900 RPM, and we're getting our spark timing between these two data points reported at 17.6 degrees of advance. If I go here to my idle advanced settings, using idle advance on, if I go to something like RPMs, we're going to be seeing apply as, adder, or set value, and then we're going to be seeing that we go to idle advance when, and then we see condition is manual or closed loop PID. Now, I typically avoid using the closed loop PID unless I'm going full closed loop with my idle control. So typically I set this on manual. So what we're going to be finding here, it's going to go in and use this idle feedback for our ignition trim we're going to be seeing here. If we're below 2% throttle, which is I'm at 1.8, my RPM is below 1,000. We can see I'm at 883. Load is over 40%. My load right here is 76 kPa. Coolant temp is above 140. My coolant temp here is at 177. And after a delay of 2 seconds. And this is going to help us if we're transitioning, let's say we're revving our throttle and it's coming back into idle, it's going to be waiting this long before it actually kicks in and does anything. Now you might want to drop this down to something like 1 second or even a half second. Might be more useful here. And you also might set your RPM as below. If you want your target speed at something like 900 or 1,000, you're going to be finding that you probably want to set this to something like 1,200. Let's go ahead and burn. And we're going to be seeing that the coolant temp above 140 is sufficient. The load is above here, 40 kPa. That'll be sufficient in most cases. You have to be noting whatever your vacuum is pulling on your engine at idle with whatever the cam and injector setup you have. You can set this accordingly. You always want this a little bit below your idle, whatever your map sensor is reading at idle. So if you're pulling, let's say, 55 kPa, 40 would be sufficient. If you're pulling something like, let's say, 40 kPa, you probably want to go bump this down to say something like 30, just so you have enough range. Let's click burn. Now what we're going to be finding here, it meets the conditions, and we can see our ignition timing is reported at, it should have been around 17, and we see it now it's 22.6. And that's coming from this table, this adder table. So let's bump up here. Now that we enabled this, we can see idle RPM advanced timing, and we can see now that, opening this up a little bit here, we're going to be seeing that this is setting an adder. So it's adding to the value here based on whatever RPM is at. So we can see at 600 RPM, it could add, let's say, 20 degrees. At 800, it can add 15, and at 925, it'll add 0 degrees. So meaning it's not going to add anything on top of whatever the values here in the table. Now we're at 883 RPM, so we're going to be interpolating between this 15 and the 0 point here. So if I bring my RPM up a little bit, let's go ahead, I'm just going to sneak it up here a little bit. We're going to be seeing that as I'm going up in idle RPM, we can see that our ignition timing is tapering back to almost what this table value is because we're going to this 0 point here. We're still interpolating between 15 and 0 because we're at 921. So that's why we're not getting all the way back to just table timing. Now what this allows us to do, depending on what our idle RPM's at, if we start to dip low in RPM, this can go and bump some ignition timing in and add it to whatever we have in the table. So what we want to find when we're setting all this up and making sense of this is that we want to have our idle ignition timing to give us the lowest vacuum possible here. So if we keep increasing our ignition timing, we're going to be finding that our map sensor here will drop lower and lower in vacuum. So we might go and bump the timing in 2-3 degrees, and we might go from 77 kPa to 70 kPa. We want to find that balance point to get our desired idle RPM here and a good low vacuum reading from our map sensor. Once we found that from our actual table values here, so looking at our breakpoints, 70, 700, 900, 1200 RPM, we're going to manipulate the values in here to get our idle speed, get our map sensor nice and low so we're getting close to maximum brake torque or close to it and achieving again that speed that we want. Then we can use this as a means of an anti-stall effect. So let's just say I want my idle at 950. I'd put a breakpoint here, let's say at 950, and I would go in at 800. I'd set one lower than that, maybe 600. I'd go and get really aggressive. I might even take this to 25 degrees. So if I started to drop in idle RPM, I'd go in and bump 25 degrees more timing in it. It would add 25 degrees onto the value in the table, and that would immediately increase the torque and bump my idle speed up. And we're going to be finding here that at 800 it would add 15, and then at 950 we'd be zeroed out. Now the opposite's going to hold true. If we start to overshoot, let's say if we go from 180 degrees to 200 degrees, we might find that our idle speed starts to increase because the values in the table are feeding it enough airflow, or enough airflow from our throttle position stop, and the idle timing has enough torque that our idle speed might increase. So if we start to overshoot and go over, we might want to go in and put some negative values. That's going to retard the timing from our table value. So if we overshoot our target of 950, I'd go in here, maybe type in something like -5 degrees, and then at 1100, type in -10. And I have to be mindful that we set this ignition trim values below 1200. So our last breakpoint here would definitely be something maybe like 1200. Click burn, and then we have that kicking into place. So now, depending on what my RPM is going to do at idle, we're going to be seeing here if we start to drop low in our idle speed, or drop high I should say, it's going to be varying our ignition timing. If we see our idle speed starts to go down here, we can see that our ignition timing starts to increase, which is going to increase the torque. If we go high in our idle speed, we start to get too high, it's going to go and retard that timing. We can see it bump the timing down, which will reduce the torque, which then in theory will then go ahead and bring our engine RPM down. And what you're going to be noticing at idle, you're going to be seeing that if we're maintaining an idle, your idle ignition timing is going to vary. If you ever look at an OEM car, we're going to be seeing that the OEM manufacturers implement this type of idle ignition feedback in all of the idle control strategies because it's going to be very effective. And we can find that it's sometimes more effective and quicker to change our ignition timing than to go in and try to mess around with our actual duty cycle. And that's why I leave my duty cycle close to 0 or at 0 and purely have my engine idling based on my airflow coming in from my throttle stop and my throttle body, and going in and using this idle ignition feedback. But again, it's going to be relying on having your idle control values here dialed in pretty well. So you're getting your idle control that you're desiring, and without having any feedback. Set that as your feedback point, your 0 point, and then doing this plus or minus ignition timing from that will allow you to bump it in. Now, again, get real aggressive as you go down, prevent anti-stalling, and be a little bit more ease when you're pulling the ignition timing out here. You don't want it to bog out the engine, but this should be really, really good values to kind of populate, noting whatever your desired target idle speed is going to be. So it's pretty straightforward to set up our idle control. One thing that I can tell you that you definitely want to keep in mind, if you're going in and you're increasing your throttle stop to get that warm idle speed set without having our percentage duty cycle having any effect, make sure that you go into tools, recalibrate your throttle position. That's going to go in as you turn that throttle screw up. It's going to go and increase your TPS reading, which then could kick you out of this adaptive idle control. If we jump in here under advanced settings, remember that we have TPS is below 2%. We can see it's at 1.8. So once you do that and you follow that, you'll be all set. Okay, so now let's jump back into our idle control in this settings tab, and we went over the pulse width modulated values and what they meant. So let's go into the stepper motor type. So let's jump in here and let's select stepper valve. Now you can see all the pulse width modulated idle control things drop out here. We're going to be seeing that now we're only able to edit anything related to our stepper motor. We also can see that we have to go ahead and take a power cycle. So let's go power cycle our box right now. Be patient while it does that. Let's go ahead, I'm going to power it up. And I forgot to hit burn before I shut off my Megasquirt, so it gave me an error. Wasn't happy with that, so it just burned that change that I made there, going into a stepper valve type from the pulse width modulated. Now we can see once we select the stepper valve type, if we jump in here to our idle cranking table, we're going to be finding that the duty cycle is now replaced with steps. So we're going to be seeing that we have the amount of steps that the motor should take in order to increase or decrease the airflow into our engine. So the higher number of steps, we're going to have more airflow. The lower number of steps, less airflow. So we can see under our cranking now, we have these in values of steps. If we jump into our warm idle control values here, we can see the IAC steps here, something like 40. So we're going to be seeing that it has this as a axis now, and that's going to be what we're working with here. So what we have to do in order to look at this with step values, we have to right click here on our gauge, go to outputs, and instead of looking at our pulse width modulated percent, we have to go to idle step position, and we're going to be looking at that in units of steps again. So let's click burn. So what we're going to be finding here is we have a time step size, and this is going to be looking at the time between each step. Normally we can leave this a value of 3. We're only going to be increasing this value if we see that the idle control or the stepper unit values here are intermittent in the reading. Let's say for going at 30 and it bumps to 60 back to 40, we might have to increase this value here. Our initial time step, this is going to be the length of time it takes for the first step of the movement. We're only going to make this a larger value here to promote a little bit more stability in our idle control. Normally we can just try it with the value that's there, it's populated. We're going to be finding next the minimum number of steps to move, and we're going to be only increasing this if we find that we're having instability as well. We're finding that it kind of pans around and it's not very stable. We would change it from the default of 1. So normally we can leave 3, 5, and 1 alone here. We're going to be finding next our homing steps. This is going to be how many steps the motor needs to make to return to its home position. 250 is typically going to be sufficient here of a value. If you get a spec sheet on a certain kind of stepper motor, you might find that it's going to specify that. Oftentimes DIY Auto-Tune will have base maps for particular types of control. So you might find if they're on the DIY Auto-Tune's website, they'll have a base map, something for like a Toyota Supra. We're going to be finding that has a stepper motor on it, and it's very specific in the number of steps, and we can populate some of this data from some of those plug-and-play base maps if we're controlling, let's say, a Toyota Supra engine, 2JZ or 1JZ, with that stepper-style motor. We're next going to be looking at homing direction, and this is going to be the direction that it's going to need to return to the home. We can see we can select either closed or open, and typically we're going to be leaving this on closed. We're next going to see this crank to run taper time. We're going to see it's 5 seconds, and that's going to be, again, when we looked at the pulse width modulated example, how much time it's going to be taking in our cranking mode, looking at our number of steps, to transition into our warm-up table here and go to the value here of number of steps. So it's going to be how much time it's going to be transitioning between those two. Let's close this and jump into here. We have a hysteresis. This is going to be in degrees, so it's going to be looking at this kind of change, a 5-degree Fahrenheit change, before it's going to go in and apply any step changes here from our lookup table. That's going to provide a little bit more stability so that we don't have oscillating idle, because our steps might be bouncing between some values from the table here. So we'll usually keep that at a value of 5. We're going to be seeing connection. Right now it's set it off. On this particular box, on my Megasquirt box that I'm using, I usually have to go in and use all my spare outputs that I have available to me. So depending on what I'm going to do with my Megasquirt, depending on what I have wired into my Megasquirt for features or for things of that nature, I might have to go in and use some of these spare things we find here. So we may or may not have to set that up, but for the connection we have to specify what we're wiring our stepper to. So we have to specify the actual wires here and connection type. We're also going to see power between steps. We're going to be finding that we have moving only, hold current, and always on. Now we're defining moving only is going to be only turning the power on to the stepper motor every time it goes between steps. This is usually the most unreliable option. We're going to be finding hold current. This is holding the current when it's applying between the changes in steps. That's typically what you want to set it on. We also find always on. This is going to be always keeping our current running for that motor. Typically, we're not going to have that. We're just going to leave it on hold current on most situations. Let's click burn here. So let's go ahead and power our box down real quick. It's asking us to do a power cycle. Let's power it back up again. Let's just quickly take a look at this. Now the idea behind this is going to be essentially the same as what we found with our duty cycle. So if we jump into our, right now I'm in my actual warm-up duty here. I'm at my 160 coolant temp. I'm above that threshold at 175 right here. We can find my steps are at 40. We're going to increase the value of the steps to increase my idle speed. So if I'm interested in maybe idling at, let's say, 1050, I might go in here and bump this up to something like, type in 55 or maybe even 60, and we're going to be finding that our idle speed should then increase a little bit. And again, we're an open loop, so there's going to be no correlation to the actual steps and any kind of feedback coming from our Megasquirt. So it's really, really simple. Now if we shut our engine off, let's bring it down into cranking. We're going to go ahead and we're going to be seeing that our steps here jump to 102 because it's coming from our table right here. We're going to see that 175 coolant temp, I'm at 175. I have specified here 102 steps. That's the position of my stepper motor to give me that requested amount of airflow that I want to allow me to start quick. And then we're going to be finding once we crank and fire the engine up, it's going to be tapering from 102 down to a value of 60 here. So let's go ahead and crank the engine over, and let's get it to fire up. Let's go ahead, crank, and let's fire it. And now we can see that it transitions from 102, and we can see it over 60 steps. So it's going to take 5 seconds approximately to go in and have that transition occur. And again, that's coming from, let's be very clear here, idle control, this crank to run taper time. That's where that value is coming from. So it's pretty straightforward how this is going to work. If you need more cranking airflow, if you find that you have to put your foot on the throttle, you can either go in here, raise the step values, or you're able to go into your cranking fuel. If you jump into here under your priming, or your cranking fuel, I should say, not priming pulse, and you could lower the value down. So you might need a little less fuel at the same amount of airflow, whatever the stepper position's at. And if you fire off the engine and it revs really high, and then it comes down again over this period from this cranking step to the actual step position where it's going to be running at normally in this table here, or warm-up position, we are going to be lowering the value down here. If we have too much of a flare effect as it starts up, we just have too much cranking steps, so we might have to lower the value. Pretty straightforward. You can experiment with what's going to work best for you, but again, we're going to be implementing, even with the IAC steps here, we're going to be wanting to, let's go ahead and burn these two maps here. It's showing we have to burn them. We're going to, again, keeping in mind that we want to go in and utilize this idle advanced timing like we found before, and it's going to be feedbacking in. So we want to run the lowest amount of steps here to really have no effect, or much to no effect on our idle when it's warm, and we really want to take that idle to get our idle speed where we want it to be, based on setting our throttle stop on our throttle body, recalibrating our TPS, and then making sure that we're hitting the actual target RPM with our ignition timing only, and really little to no influence from our idle stepper position, so our idle is as smooth and stable as possible.
Okay, so that wraps up Megasquirt training part 15. In the next video, we're going to be taking a look at our closed loop idle control. We're going to have a lot to learn, so I'll see you in the next video.